Hello, today we'll be doing limits and continuity. So just to point out that section 4.2 would be the section in the Stewart textbook, and section 4.2 would be the section in the Calc 3 book in OpenStax. All right, let's get started. All right, so material in this section is from Active Calculus Multivariable by Steve Schlicker, David Austin, and Matt Bolkins, 2017. The Active Calculus book is licensed under the Creative Commons Attribution Non-Commercial Share Alike 3.0 unsupported license. Okay. So first of all, we're going to start with motivating questions. What do we mean by the limit of a function of two variables at a point a, b? What techniques can we use to show that a function of two variables does not have a limit at a point a, b? And what does it mean for a function of two variables to be continuous at a point a, b? All right, so limits, not limits, and continuity. All right, learning objectives. Calculate the limit of a function of two variables. Describe how a function of two variables can approach different values at a boundary point depending on the path of approach. State the conditions for continuity of a function of two variables. Verify the continuity of function of two variables at a point. All right, first of all, preview activity. We investigate the limits of several different functions by working with tables and graphs. All right. So consider the function f defined by f of x equals 3 minus x. And it says complete table 1. Of course, table 1 wasn't filled in. So you basically go into your calculator and you type in x equals minus 0.2. So here I can show you on an online calculator. Let's see, we can find one on Google. So let's see there, online calculator. And so I like Desmos, but you can even use this one here just on the web. So 3 minus 2, right? Minus 2. And so with that, was that the, hold on, am I entering the right function? It's 3 minus 0.2. Okay, so I made a mistake. So it's 3 minus and then minus 0.2. And so you get 3.2. All right, so let's go back to our page. And then you see that at x equals minus 0.2, you get f of x equals 3.2. Okay, good. So you do the same with x equals minus 0.1, x equals 0, x equals 0.1, and x equals 0.2, and then you get your f of x. So I'll use for those. And here are the solutions. Now, what does this table suggest regarding the limit as x goes to 0 of f of x? So that's the question. All right, so let me see. Well, I have 3.2, 3.1, and then goes to 3. So it looks like in this direction, my f of x is going towards 3. And so this would actually be the limit as x goes to 0. And from what side? From the negative side. So from the left side, it goes to 3. Now let's look on the right in this direction. So what's happening here? So limit as x goes to 0 from the positive side, so we're going down, x is 0.2, 0.1, 0, and so forth. We are looking at the y values getting closer to 3. So again, from the right-hand side, you get the limit is going to 3. So that means if both of the limits from both sides are equal, then we can say that the limit as x goes to 0 of f of x is identically equal to 3. All right. I should probably delete my annotations. Okay. Go on to the next page. All right, so explain how your results in A are reflected in figure 1. Okay, well, here's figure 1. And we see that we had limit as x goes to 0. From the left-hand side, we were approaching 3, and that's what we're seeing in this line. We're approaching 3 from the left. And we also found that the limit as x goes to 0 from the right-hand side of f of x, there's f of x, is also going to 3. So yes, in fact, from the left and from the right, we are approaching the value f of x equals 3. Let's continue. So next, consider g of x equals x over absolute value of x. Complete table 2 with values near x equals 0, the point at which g is not defined. We know g is not defined here because at x equals 0, you would have denominator 0, so that's how we know that. All right, so using an online calculator or your scientific calculator, again, or actually just a basic calculator, you can plug in these x values, just like we did for the previous problem, and then calculate what your y values are. Or you can notice that x over absolute value of x is basically the sine of x, right? Because you have x on the top, you have x on the bottom, except you're taking away the sine of x from the bottom. So it's really just, you're canceling the x's and leaving just the sine times 1. Okay, so here you have, for x negative, you're going to get a negative from the top, and then the x's are going to cancel, and so you're going to get negative 1s. So let's just write that out. Minus 0.1 over 0.1, and so you're just going to get minus 1. But that's okay if you want to do it on a calculator too. And then on your right-hand side, you have positive x's. So here, let's do this one. Then you have 0.01 over 0.01. So of course, you're just going to be left with 1. Now notice these first 3, all the negative ones are all negative 1, and your right 3 are all positive 1. So that is not continuous, right? And we already know that at x equals 0, we don't have continuity. So what does that mean as far as limits go? Okay, well, that means that the limit does not exist, because from the left-hand side, we have a different limit than we get from the right-hand side. And so that's basically all we're saying here is the limit does not exist. Okay, so explain your results in C, how your results in C are reflected in figure 2. Okay, well, as I was saying, you have the limit coming from the left. So limit, maybe I'll write over here, limit as x goes to 0 from the left-hand side of f of x, you're getting equals to minus 1, whereas the limit as x goes to 0 from the positive side of f of x, you're getting equal to 1. And you can see that in the picture. You have your 1 up there and your minus 1 down here. Now, those two things are not equal. They're, in fact, quite far apart. And so you conclude again that the limit from the left does not equal the limit from the right. And so the limit does not exist. Okay. Now let's examine a function of two variables. So let f of xy equals 3 minus x minus 2y, and then it says complete table 3. So here, down this column, this would be x. So this is the x values. And then in the top row, you have the y values that you would compute. So let's, I'll just do one computation. So let's do this one, for example. So let's say that's x equals 0, and then what is that, y? So x equals 0 and y equals minus 1. And so you would calculate f of 0 minus 1 is equal to 3 minus x, so x is 0, minus 2 times y, but y is minus 1. And so there you're going to get 3 minus 0, so that doesn't bother us. And then minus 2 times minus 1 is plus 2, so 3 plus 2. Oops. So 3 plus 2 is equal to 5, and that's how you end up with that number there. So you continue in that way for all the x values and all the y values in the table to fill up the table. And that's basically it. Okay, so now that you've got this, you ask, what does the table suggest about the limit as xy goes to 0, 0 of f of xy? Well, let's try and look at the picture or at the table and see if we can figure that out. So I'm going to focus on one column and see what happens as we approach 0, 0. So that's this one. Maybe I can use a new color. Let's go green. So 0, 0. So that's this y value, and then 0, 0 on the x value. So that's 0, 0 there. And so really what happens as we're approaching this? Well, I can see that as we're going down in this direction, we're approaching 3. So limit coming down is approaching 3. Limit going up, okay, in this direction, I also see I'm approaching 3. How about in the this direction, right? So if I hold x fixed and I vary y, I can see, we could probably have some more y values to see it more clearly, but again, I'm seeing these values approach 3, and from the left, so holding x fixed, coming from the right, I can also see that these numbers are approaching 3. How about the diagonals? Let's take a look. 6, 3.33. So in this direction, I'm also approaching 3. Also in this direction, it looks like I'm approaching 3. And I think you get the idea. It looks, from this table, it looks like we are approaching 3 from all the different directions. Okay. So the limit when, or that's what we're thinking, the limit when approached from each direction is 3. Okay. Now let's look at a picture. So left is the graph of f of x, y equals 3 minus x minus 2. I know you can graph your own functions in these 3 dimensions using any online grapher, and I'll do that in a little bit with one that I found a little bit cumbersome to look at the picture. And then the right is what we call the contour plot. Okay, so explain how your results in E are reflected in figure 3. Compare this limit to the limit in part A. How are the limits similar and how are they different? So let's recall part A. Part A was just a one-dimensional function, right? We had the 2 directions, the limits existed and they were the same, right? And then the table, we're actually seeing that the limits from all these directions are the same. So that would make us want to tend to think, yeah, that then must be correct. So the similarities are both the limits exist. And then the difference in E, the limit needs to be approached from different directions, of course, because you have, you know, x from negative, positive, and then you have y, negative, positive, and you have like both of them being positive, both of them being negative, and then a combination of the 2 things, right? So you have a lot of different more directions than just 2. All right, so let's go deeper. Let's look at another function. We're a little bit more complicated now. G of xy equals 2xy over x squared plus y squared. So let's look at this function. So do I want to graph it now or later? Later. All right. When you look at this, you can see that when x is 0 and y is 0, it's not defined, right? So this function is not defined at 0, 0. Now it says, let's complete table 14.2.7 and then round to 3 decimal places. All right, so again, you have your x values here, right? And your y values are along here. And then you can just use your calculator online or your calculator hand to calculate these various numbers. Now, you see a lot of similarities, right? You're only seeing ones, 0.18, minus 0.18, and 0. And that's it. And then at 0, 0, you have undefined, of course, because when x is 0 and y is 0, that function is not defined because you can't divide by 0. All right, so let's see, what does this mean? So we're actually being asked here, what does this suggest about the limit as xy goes to 0, 0 of g of x, y? So what does that mean? Okay. So let's think about that. So what does that mean? So let's see, as we approach 0, 0, well, for y equals 0, you just have the function is 0, 0, except at that point. Coming from when x is 0, you have the function is 0 coming from the left, coming from the right. But they're not, it's certainly not an existing limit, right? You don't have the things agreeing from left to right. Also, let's look at the diagonal. On that diagonal from the left here, I have 1s, and then it hits undefined. On the diagonal on the bottom, I have -1s. So it almost looks like, so if I can draw these, if we didn't have that undefined in the center, it almost looks like these limits are the same on both sides, right? But not this one, right? So yeah, so it looks like the limit does not exist, right? Okay, so that's pretty much all I would say. The limit does not exist. Okay, so just, that's what you conclude, or that's what we conclude. Okay. Now explain how your results are reflected in figure 4. Compare this limit to, compare this limit to the limit in part B. Okay, so part B, right, that was a function in one variable, and we saw that the limits did not exist. Now, when I look at this picture, I have to be honest, at least the one on the left, I am not seeing it. So I'm a very visual type person, and yes, of course, this is very visual. Anything written is visual. We can see something, but I'm not getting that the limit doesn't exist from this picture. So I'm just going to go ahead and graph that function for myself. And that's what I encourage you do. Anytime you're not really sure, you just want to make real sure that you're doing your calculations correctly, especially down the line when we do derivatives, I recommend you to graph things and really analyze them a little bit. So let's graph this function 2xy over x squared plus y squared. So I'm going to go and search for an online 3D grapher. And then what do I get? Look, you can see you have all of these different options. Some of them I tried, I just didn't really click with the program. I seem to click best at the moment with 3D GeoGebra. That changes sometimes. Sometimes I find another program I like better. Right now, I'm feeling like this one works for me. So here, you can either write f of x, y. I like to write z is, and then I'm going to go ahead and type in that function. So 2xy divided by x squared plus y squared. Okay, I think that's it. Okay, and then now I'm going to look at this picture and see if I can gather, you know, the conclusion that I just made analytically, right? So I'm moving it around. There's no one right way. Just taking a look and seeing what I see. Okay, and plus it looks like the x and y isn't really differentiated here. So there might be other graphers that you might like better where it makes it a little bit clearer, but that's okay. Here x and y seem to have a similar effect. What I notice is it kind of pinches in the middle, right? At 0, 0. Kind of pinches. All right. So what else? What do you see down here? You have this pinch at the bottom, goes up and in. Yeah, so I'm not seeing the same things coming from the, I can't say left-hand side. Let's looking at the gray part. I'm not seeing the same limit coming from this side as I do from this side on the top. So let me, I can mark this up with red. So the limit here on this area, this is going to 1. And the limit in this area, it looks like it's going to -1. Okay, so that's what I'm seeing. So let me move it around a little bit more. Okay, so yep, I see the blue bits, they're going to 1. But when I focus on those gray bits, they're kind of coming down. Okay. All right, so I think that's probably enough from that picture. Let's go back to the notes. Okay, so how are the results similar and how are they different that they're asking, comparing? So in B, the limit is evaluated as x goes to 0 along a line. And then in H, the limit is evaluated along different lines, right, as x, y goes to 0. Okay, so all right, so now let's go into a little bit of theory and then more examples, or more activities actually. So limits and functions of two variables. Given a function f of xy, we say that f has a limit L as xy approaches a point AB, provided that we can make xy as close to L as we like by taking xy sufficiently close but not equal to AB. So we write limit as xy goes to AB of f of xy equals L. So activity 1, consider the function f defined by f of xy equals y over square root of x squared plus y squared, whose graph is shown below in figure 5. Let's take a look at figure 5. I might want to graph this one too. Yes, I think I will in 3D. If f, or is f defined at the point 0, 0, what, if anything, does this say about whether f has a limit at the point 0, 0? So first of all, f is not defined at the point 0, 0, right? So not defined at the point 0, 0. And the limit does not depend on whether or not a function is defined at a point. So that's different to what I was concluding up here. Well, partly. Okay, so notice that. So given a function, we say that f has a limit L as xy approaches AB, provided that we can make f of xy as close to L as we like by taking xy sufficiently close but not equal to AB. Okay. All right, so B, values of f at 3 decimal places at several points close to 0, 0 are shown in the table 5. All right, so here we are. What do we see? So we don't know what's happening at 0, 0. Well, we know it's undefined, even though it's not in the table. And then we can see that along y equals 0, it's just 0. Okay, so that's the limit there. But hold x fixed at 0, okay, with the exception of y equals 0. And then you have the limit there is going to -1 from the left and 1 from the right. And then you see something interesting on the diagonals. You have, on the diagonals, you have minus 0.707 from the top left. And from the bottom right, you have 0.707. And also the top right, 0.707. And then the bottom left, minus 0.707. Okay, so based on these calculations, state whether f has a limit at 0, 0 and give an argument supporting your statement. The blank spaces in the table are there to help you see the patterns, which we just discussed. So here, what we're saying, or what we're observing, is that as we approach that center point from different directions, the limit does not exist. Okay, I just want to rewind to this previous problem before we got our theory for a second and look at that table. And also, as we were approaching the same problem from different directions, we had different numbers, so the limit does not exist. Okay. All right. So let's go on. So part C. Now we formalize the conjecture from the previous part by considering what happens if we restrict our attention to different paths. First, we look at f for points on the domain along the x-axis. That is, we consider what happens when y equals 0. What is the behavior of f of x, 0 as x approaches to 0? If we approach 0, 0 by moving along the x-axis, what value do we find as the limit? Well, if we set f of x and set y equals to 0 in that function, and that's just the numerator is going to take over, we're just going to get 0. And so also limit as x approaches 0, 0 is still 0. Okay, now D. What is the behavior of f along the line y equals x when x is positive? All right, so that is when the value of f of xx when x is positive. If we approach 0, 0 by moving along the line y equals x in the first quadrant, thus considering f of xx as x goes to 0, what values do we find as the limit? Okay, so this is where we would actually take the function. So let's look back at the function again. So we have the function is y over square root of x squared plus y squared. Okay, so let me just write that down. So f of xy is y over square root of x squared plus y squared. But then if we're going to replace the y with x, so that's f of x, that equals to x over square root of 2x squared. Okay, so that equals to x over square root 2 times x. Okay, the x's cancel. It's not defined at 0, of course. So you're getting 1 over the square root of 2, which is 0.707. Or that's to 3 decimal places. Even though at x equals 0, it is not defined. Okay. So here we go. Now we formalize. In general, if limit as xy goes to 0, 0 of f of xy equals L, then f of xy approaches L as xy approaches 0, 0. Regardless of the path we take in letting xy goes to 0, 0. Explain what the last two parts of this activity imply about the existence of limit xy going to 0, 0 of f of xy. Well, we concluded that the limit does not exist because we found different values depending on which path we approached the point 0, 0 in both functions. All right. Shown below in figure 6 is a set of contour lines of the function f. What is the behavior f of xy as xy approaches 0, 0 along any straight line? How does this observation reinforce your conclusions about the existence of limit as xy approaches 0, 0 f of xy from the previous part of this activity? Use the fact that a non-vertical line has an equation y equals mx for some constant m. So the limit is different depending on the direction of approach, is what we're concluding. So you can also do that exercise of plugging in y equals mx, like I just did in the previous part. So you can run through this activity as well. So you can do y over square root of x squared plus y squared, and then replace the y with x m or mx, and so you're going to get mx over square root of x squared plus m, and so you're going to get m squared plus x squared, and so then you can do mx over, you can factor out the x, so x over the square root of 1 plus, 1 plus m squared. You can cancel out the x's. Okay, and you see the idea. You get m over square root of 1 plus m squared on the bottom. And then basically, you've got a different value for every different m. So that's how you end up with that conclusion. Okay, so the limit is different depending on the direction of approach. Okay, so as a general rule, we must have limits along different paths. If f of xy has two different limits as xy approaches a point a, b, along two different paths, then the limit as xy approaches a, b of f of xy does not exist. Activity 2. Consider the function g defined by x squared y over x to the 4 plus y squared, and investigate the limit xy going to 0, 0 of g of xy. All right, what is the behavior of g on the x-axis? That is, what is g of x 0, and what is the limit of g as xy approaches 0, 0 along the x-axis? So then you would just literally plug in y equals 0 into this function g of xy. And so you would get a 0 on the top and then the x to the 4 on the bottom. So it's for different values of x. So that's just 0. And so taking the limit as x goes to 0 of 0 is 0. Now, what is the behavior of g on the y-axis? So similarly, if you plug in x equals 0 here, you're going to get 0. So g of 0y equals 0. So g of 0y already equals 0. So the limit as y goes to 0, right? It's not going to affect it. It's still going to be 0. Okay. Okay, what is the behavior of g on the line y equals mx? That is, what is g of x mx? And what is the limit of g as xy approaches 0, 0 along the line y equals mx? So it's similar to what I just did. Plug in mx for y, and that's what you get here. And so you then get mx cubed over x to the 4 plus m squared x squared. And then when you factor out the x squared from the top and bottom, you're left with mx on the top and the x squared plus m squared on the bottom, because these x squareds, they cancel out. All right, based on what you have seen so far, do you think limit as xy goes to 0, 0 of g of xy exists? If so, what do you think its value is? So far, so let me now rewind because my memory is like this little. Let's see. So we're talking about when x and y is 0. So based on what I've seen so far, it looks like the limit is 0. I'm a little hesitant because I'm not really sure, but that's what it seems like to me. It looks like it's 0, right? So if we come along x, if we come along y, if we come along a line mx, it doesn't matter what m is, as you approach x is 0, right? It looks like, yeah, as long as m is not 0, right? You can't start at 0, 0. So, okay, so we conclude that it looks like the limit is 0. Now, consider the behavior of g on the parabola y equals x squared. What is g of x squared? And what is the limit of g as xy approaches 0, 0 along the parabola? So again, we plug in y equals x squared in the original function, and this is what we get. So we get x to the 4 up top over x to the 4 plus x squared squared. Now x squared squared is x to the 4, so you get 2x to the 4. You can cancel out the x to the 4s for x not equal to 0, of course, and then you're left with a half. Uh-oh, that's why I was hesitant. So yeah, so we had, looks like it's working, yay. But now down here, we're like, no, it's a different limit. So it does matter what path you're taking. And the reality is, for the limit to exist, it has to be the same no matter what path you take. So not just lines, just any path at all. So state whether the limit of xy approaching 0, 0 of g of xy exists or not, and provide a justification of your statement. Well, limit of xy approaching 0, 0 of g of xy does not exist. There is a different limit depending on the path taken to approach 0, 0. At the top, we had, if we went along a line, we had the limit was 0. And then if we took the parabola, we had the limit is a half. And so 0 is not equal to half, so the limit does not exist. This activity shows that we need to be careful when studying the limit of two variable functions by considering its behavior along different paths. If we find two different paths that result in two different limits, then we may conclude that the limit does not exist. However, we can never conclude that the limit of a function exists only by considering its behavior along different paths. So generally speaking, concluding that a limit lim xy approaching ab of f of xy exists requires a more careful argument. So you have to think more. Okay. So using methods learned in the first quarter of calculus, find the limit as xy approaches 0, 0 of x squared minus xy over square root of x minus square root y. Now, some of you might guess this, some of you might not. I've spent a lot of time in the last year or two teaching algebra, so this is fresh on my mind. When I see those radicals on the bottom, immediately I think about rationalizing. So rationalizing, what does that mean? I see the root x and the root y, so I have to multiply top and bottom by root x, basically the conjugate. So root x plus root y, or basically the denominator with a change sign. So root x plus root y, because I know that's exactly what I need to multiply to get rid of the radicals in the denominator. So this is already pre-typewritten, that's just what I wrote. So you go ahead and multiply that out, and so you do, your foiling and so forth for the top. And so then, well, you can do the foiling. Hold on, you know what? Scratch that, scratch the foiling, because we're gonna want to cancel some stuff. So this took a little bit of experience. So instead, factor out an x. So factor out an x here. And then leave the x minus y alone, because when you FOIL out here at the bottom, you know that you're going to end up with x minus y on the bottom because you're getting rid of the radicals. And then at this point, you can go ahead and cancel out the x minus y's. And cancel the factor x minus y because the path y equals x, along which x minus y equals 0 is not in the domain of the function. So that's why you're allowed to do that. And so you're left with the limit as xy approaches 0, 0 of x, or of the function, is equal to x times square root of x plus square root of y. Okay, so now what can we say about that limit? It's 0, right? So the limit is 0. So after all this, you should be able to say equals 0. So no matter which way you're approaching, no matter what y I plug in there, you're going to approach 0, 0. Okay. Okay, so continuity. Recall that a function f of a single variable x is said to be continuous at x equals a, provided that the following three conditions are satisfied. So continuity, not that the limit exists. F of a exists, limit as x goes to a of f of x exists, and limit as x goes to a of f of x, it has to be equal to the function f of a. Okay, so that's continuity. So using our understanding of limits of multivariable functions, we can define continuity in the same way. Okay, so definition, continuous function of two variables. A function f of xy is continuous at the point ab if f is defined at ab, limit as xy approaches ab of f of xy exists, and then limit as xy approaches ab of f of xy is equal to f of ab. A function is continuous if it is continuous at every point of its domain. Okay, so this is basically just pointing out, if you have continuity at every single point in the domain, your function is continuous over the entire domain, versus in comparison to a piecewise defined function. Okay. All right, so this is where this video ends. I do recommend you to watch these two videos here just to learn and understand a little bit more. Thank you very much.